So we've talked about all the aspects and all the characteristics associated with functions that we need to understand and know at advanced higher. What we now have to be able to do is bring everything together and be able to sketch more complex functions and polynomials so that we can gauge what they look like a lot better with more accuracy and detail involved. Now this includes looking at turning points, looking at asymptotes, looking at the behaviour of the graph as x tends toward positive and negative infinity, and what the behaviour of the graph as y tends towards positive and negative infinity looks like. We have to be able to add all of this detail in, and we have to be able to do these sketches accurately. So what we need to be able to do is do these more complex functions off the tip of a hat, i.e. as quickly as we possibly can. And in order to do this, what I want you to do is ask yourself 5 key questions to get bits of information which we can then use and bring together. So first things first, I want you to figure out the intercepts. So we need to figure out where it cuts the y-axis. If we remember back to higher, that's where x is equal to 0. We then ask where does it cut the x-axis, and that's where y is equal to 0. So that's the first set of questions. We need the intercepts. Second one is where is the function increasing, where is the function decreasing. For that, we have to look at the derivative of both. And for a function to be increasing, derivative has to be bigger than 0. For a function to be decreasing, derivative has to be less than 0. So we have to look at that. We then want to know when is the curve stationary. So where are the stationary points? That's the third thing we then start to look at. And we should know that at that point, the derivative equals 0. We then have to look at points of inflection and concavity, i.e. is it maximum or a minimum. And this is where looking at the second derivative comes into play, f double dash of x, and looking at its behaviour, where it's bigger than 0 or where it's less than 0. We have to then look at points of inflection. We know how to do that. Tables of values could be helpful in these situations, but second derivative really is what we want to be able to do. We then want to ask ourselves, what are the non-horizontal points of inflection? Do any of these exist, and what do we have to do to get them? And in that case, what we ask ourselves is we look at points where the second derivative is equal to 0. So we have to calculate where they exist, and that's the non-horizontal points of inflection. The last one we then want to look at is the asymptotes. So where are the vertical asymptotes? Where are the non-vertical asymptotes? So we need to be able to do these. Now, vertical asymptotes, we know that's when the denominator of the fraction is equal to 0. The non-vertical, that's their behaviour as x tends towards positive and negative infinity, and that's where the partial fractions and splitting it up comes into play. That's what that helps us to do. So I'm going to show you an example, how to approach each of these, and then how to bring it together as a sketch. So what I'm going to do is I want to sketch the curve of f of x equals x minus 2 over x plus 1. So the first thing we ask ourselves is the intercepts. So if I look at the y-intercept, what I know is that all the way up the y-axis, x is equal to 0. So if I substitute that in there, I get 0 take away 2 over 0 plus 1. I know the curve is then going to cut the y-axis at y equals negative 2. For the x-axis intercept, what I know is that y is going to be equal to 0. Now for this function here to be equal to 0, the top of the function has to be 0. So what that means is in this case, x minus 2 has to equal 0. And if x minus 2 is equal to 0, x is equal to 2. Second question we then ask ourselves is when is the function increasing, when is the function decreasing? And in order to do that, we have to calculate a derivative. Well, if f of x is x minus 2 over x plus 1, f dashed of x equals 3 over the x plus 1 squared. Now, I've done that using the quotient rule. Go and look at that video and come back and just make sure you can get your head around going from there to there, but it's an easy jump. What I then have to do is look at when this function is increasing and decreasing. Well, the denominator is a square number, so regardless of what value of x I put in there, I'm always going to get a positive. The top is 3, so that's always going to be positive. So what I can say is that f dashed of x is greater than 0 for all x. So I know the function is always going to be increasing. It's always going to have that increasing look about it. It's never ever going to decrease at any point. Great. So that will help me with the shape. The third thing I then have to ask myself is where my stationary points exist. So for the stationary points to exist, f dashed of x equals 0. Well, here's my derivative here, and for it to be equal to 0, the top line has to be equal to 0. But in this case, my top line is always going to be 3, so in this case, f dashed of x can never be 0, so I'm not going to have any stationary points on the graph whatsoever. So there'll be no turning points for me to calculate in Sketch. The fourth thing I then have to do is look for my non-horizontal points of inflection. And we remember that in order to do that, that's with the second derivative, f double dashed of x equals 0. Well, if I take my first derivative and I calculate my second derivative from that, what I end up getting is that f double dashed of x is equal to negative 6 bracket x plus 1 over x plus 1 to the power of 4. What I then want is when this is equal to 0. And for this to be equal to 0, my top line has to be equal to 0. So negative 6 bracket x plus 1 equals 0. So in this case, x is equal to negative 1. However, if I take x equal to negative 1 and plug it in the bottom, I actually get 0. So I'm going to end up dividing by 0. So at this value, it actually doesn't work. At this value, I cannot have any non-vertical points of inflection. So I can ignore that one and say, right, so there's no non-vertical points of inflection. I now have to look at the asymptotes. So in order to look at the asymptotes, I take the x minus 2 over x plus 1 and I look at it in a bit more detail. Now, highest power on the top is equal to the highest power on the bottom. So what that means is I then have to do my algebraic long division in order to split this up. Remember, we always want the highest power on the top to be strictly less than that on the bottom. So we have to do the long division in order to get that. If I was to do my algebraic long division on that, what I'd end up getting is f of x equals 1 take away 3 over x plus 1. So now that I've got that, I can look at my horizontal and my oblique and my vertical asymptotes. So remember, in order to get my non-vertical asymptotes, so that's the oblique ones or the horizontal, what I have to look at is the behaviour as x tends towards infinity, so I focus on any parts in front of the fraction. So in this case, all I've got is a 1, so y equals 1 is going to be my non-vertical or horizontal asymptote. I then want to look at the vertical asymptotes, so where it goes up and down. And in order to look at that, that's when I focus on the denominator. So if I focus on the denominator and I set it equal to 0, I know that x plus 1 equals 0. So in this case, x equals negative 1 is my vertical asymptote. So now that I've got the two asymptotes, I have to determine how the behaviour of the curve as it approaches those asymptotes looks. So let's imagine I do just a rough sketch of those two asymptotes. I know that I'm going to have one here at y equals 1, and I'm going to have one going up and down here at x equals negative 1. What I have to do is figure out what happens as x goes off to positive and negative infinity. That'll judge my behaviour around y equals 1. And then I have to look at what happens as x heads towards the vertical asymptote from above it and from below it. And then that'll tell me exactly what happens to the behaviour of my curve. So let's imagine I'm going to do x tending towards positive infinity. So x is going up this way. What's going to happen to the curve? Well, as x tends towards positive infinity, this fraction here is going to get smaller and smaller and smaller, but it is always going to be positive. So what that means is that this is always going to be take away a positive number. So it's going to be 1 take away something. What that means is that as I get higher and higher in x, my y is going to go towards the 1 as you'd expect, but it's going to go towards the 1 from below, which is what this minus means. So as x tends towards infinity, y is going to tend towards 1 from below. So it's going to approach it going in that direction there. If I then look at the other direction, x tends towards negative infinity, what's going to happen here is my x goes along this way. What's going to happen is my fraction again is going to get smaller and smaller and smaller, but every value of x is going to have a magnitude bigger than 1, despite it being negative. So it's going to be something bigger than 1, a negative number bigger than 1, plus 1. So the bottom will always be negative, so the fraction is always negative. So I'm going to have 1 take away a negative number, which is the equivalent of 1 plus something. So it's always going to be bigger than 1. So as x tends towards negative infinity, y is going to approach the 1, just as we expect, but it's going to be above the 1. So it's going to approach it from this direction here. So there's my asymptote extended a bit. We then have to figure out what happens as I approach my vertical asymptote. So as x tends towards the negative 1 from below, so imagine I'm coming at it from this direction to get closer and closer and closer. I know, as I mentioned before, the size is always going to be negative. So it's always going to be this minus something. But as I get closer and closer to negative 1, the size of this fraction is always going to increase because I'm dividing 3 by a number that gets smaller and smaller and smaller all the time. So it's going to be 1 take away a negative fraction, so 1 plus a fraction, but that fraction itself is getting larger and larger and larger. So as I get closer towards negative 1, I'm going to continue to go up in my y direction. So as x approaches negative 1 from below, y is going to tend towards infinity. I then look at the same logic as I come down this way. So let's imagine x tends towards the negative 1, but this time I'm coming from above it. We then have to say to ourselves, what happens to y in the long run? Well, as I approach negative 1 from below, so I'm coming this direction here, the size of this number here for x is always going to be smaller than the 1. So this fraction is always going to be positive. But because the bottom, again, the size of it gets smaller and smaller, it's going to be 3 divided by a number that continues to get smaller and smaller. So that overall fraction is going to increase in size. So I'm then going to have 1 take away a much bigger number. As that number increases, y is then going to tend towards negative infinity. So it's going to go somewhere down there as I get closer and closer to negative 1 from that side. Once I've done that, I've got all the information I now need in order to be able to accurately sketch the graph and put on the key bits of info. So if I was to do that, first I'd draw my set of axes. So there's my horizontal, my vertical. I'd label them, there's my f of x, and I'd label this one as my x. We then have to start putting the information on. So first we'd start with the asymptotes. So I know I've got a horizontal asymptote that goes along there at f of x equal to 1. And I know that I've also got a vertical asymptote going up and down there at x equal to negative 1. I then think of the information I did. So I know that as x tends towards infinity, it's going to go up the way and tend towards this horizontal asymptote from below. So I know that as my behaviour for x increases, the curve is going to go up this way. I also know that as x goes towards negative infinity, I'm going to tend towards the asymptote, but this time from above it. So I know it's going to look something like that. I then look at the behaviour as I tend towards negative 1. So I know that as I go towards negative 1 from above, I'm going to go here, down towards negative infinity and f of x. And I know that as I come from below, I'm going to tend towards positive infinity. So I know that this section of the curve is going to look something like that. I also know the information in this section and how the behaviour of the curve looks, so I'm going to join these up. But I have to remember I also know the x and the y-axis intercept. So as I do that, I know it cuts the x-axis at 2, it cuts the y-axis at negative 2, so I then have to make sure that when I do the sketch, I fill those in. So we're able to do a much more accurate sketch of the curve with more key points and key information marked in. We have to make sure when we do this, all of this is put into place. We calculate every single one of the steps, ask ourselves those 5 questions, do the work in, and put all the information itself into the sketch. And if you can, maybe make it slightly neater than mine.